In this video, we will learn about inverse trigonometric functions, how to graph it, find the exact value, and use a calculator to approximate the value of an inverse trigonometric function, how to evaluate a composition, and simplify a composition involving a trigonometric and inverse trigonometric function. First, let's review the definitions of a function and its inverse. Function is a relation or correspondence that pairs each element of the domain or input with exactly one element from the range or output. We can say function is a set of ordered pairs in which no different ordered pairs have the same first coordinate. The inverse of a function is found by interchanging the coordinates in each ordered pair, that is, an element of the function. With the inverse, the domain and range of the function have switched roles. If y equals f of x is one-to-one function, then the inverse of f is also a function and can be denoted by y equals f inverse of x. Because the graphs of all 6 trigonometric functions do not pass the horizontal line test, the inverse relations for these functions will not be functions themselves. However, it is possible to define an inverse that is a function by restricting the original trigonometric functions to certain angles. We'll discuss the inverses of 3 major trigonometric functions: sine, cosine, and tangent. The other 3 inverse functions can be handled by the use of reciprocal identity. Let's first review the inverse sine relation. To find the inverse of y equals sine x, we interchange the x and y to obtain x equals sine x. To graph y equals sine x, we simply reflect the graph of y equals sine x about the line y equals x. As you can see from this graph, x equals sine y is a relation but not a function because it does not pass the vertical line test. For every value x in the domain, there are many values of y. However, if a function y equals sine x is to have an inverse that is also a function, it is necessary to restrict the values that x can assume so that we may satisfy the horizontal line test. To notice that the segment of the original sine graph passes the horizontal line test and it maintains the full range of the function in the interval from -1 to 1. And the second picture shows the graph of inverse relation x equals sine y with the restricted interval after the sine curve has been reflected about the line y equals x. It is apparent that if x equals sine y is restricted to the interval from -pi/2 to pi/2, then each value of x between -1 and 1 is associated with exactly one value of y, and we have a function rather than just a relation. The inverse sine function will return an angle between -pi/2 and pi/2 inclusive, corresponding to q4 and q1. Notation used to indicate the inverse sine function is y equals sine inverse of x, or y equals arc sine x, meaning that x equals sine y and y is between -pi/2 and 2. In words, y is an angle between -pi/2 and pi/2 inclusive, whose sine is. Just as we did with the sine function, we must restrict the values that x can assume with the cosine function as well in order to satisfy the horizontal line test. The interval we restrict is from 0 to pi. Here's the graph of the inverse relation x equals cosine y with the restricted interval after the cosine curve has been restricted about the line y equals x. The inverse cosine function will return an angle between 0 and pi inclusive corresponding to q1 or q2. The notation used to indicate the inverse cosine function is y equals cosine inverse of x or y equals arc cosine x, meaning that x is equal cosine of y and y is between 0 and pi. In words, y is an angle between 0 and pi inclusive, whose cosine is x. For the tangent function, we restrict the values that x can assume to the interval from negative pi over 2 to pi over 2. The inverse tangent function will return an angle between negative pi over 2 and pi over 2, corresponding to quarter 4 and quarter 1. The notation used to indicate the inverse tangent function is y equals tangent inverse of x, or y equals arctangent of x, meaning that x equals tangent x, y, and y is between negative pi over 2 and pi over 2. In words, y is an angle between negative pi over 2 and pi over 2, whose tangent is x. To summarize, here are the three inverse trigonometric functions we have presented, along with domain, range, and the graph for each. Now let's work out some examples on what we just learned. The first example, we need to evaluate in radians without using a calculator or the table the following examples. The first one, let's start with sine inverse of 1/2. Remember, the inverse sine function is restricted for the angle between negative pi over 2 and pi over 2 for quarters 4 and quarter 1. So the angle between negative pi over 2 and pi over 2, whose sine is 1/2, if you forgot, you can pick up at the table. 1/2 is pi over 6 in radians. In the next part, part B, we need to find our cosine of negative radical 3 over 2. Remember, the inverse of cosine functions is restricted for quarters 1 and quarter 2 for the angle between 0 and pi. So we're looking for the angle whose cosine is negative square root of 3 over 2. And such angle is, in these two quarters, whose cosine is negative square root of 3 over 2, is 5 pi over 6. Let's write it down. Let's do the third part of the problem. Remember, tangent is sine theta over cosine theta. Therefore, in order to get 1, both sine and cosine need to be the same. That will happen in pi over 4, but because its tangent inverse is negative 1, it will be negative. Let's look at the next example. In this example, we need to use a calculator to evaluate each expression to the nearest tenth of a degree. Scientific and graphing calculators are programmed so that the restrictions on the inverse trigonometric functions are automatic. That's good. But we need to make sure that we set up the mode into degree mode. So if you have a graphing calculator, go to mode and set it up into degree. Now we're good to go. Now let's do the first part. Find arcsine of 0.5075. Remember, arcsine is the same with sine inverse. To get to the sine inverse, we need to click second, go to sine, to get to sine inverse, and then enter 0.5075. Enter. Let's round to 10th. So we get 30.5 degrees. Now let's find our cosine of negative 0.5075. Go to second, sine, to get to sine inverse, and then type negative. Make sure to type negative and not the minus sign. 0.5075. 5075. Enter. We get negative 30.5. Because sine inverse function is restricted from negative pi over 2 to positive pi over 2, these two will be reference angles of 30.5 degrees. In the same manner, we'll do the rest of the calculations. Now we're using second cosine to get to cosine inverse 0.6428. Enter. Round to 10th place, which will be rounded to 50 degrees. The same manner we'll do cosine inverse of negative 0.6428. It will be 130 degrees. Because remember, inverse cosine function is restricted between 0 and pi. So these two angles, 50 and 130 degrees, are reference angles for 50 degrees. Let's do the calculations for arctangent of 4.474. To get to arctangent or tangent inverse, we click second tangent, enter 4.474, enter 77.4 degrees. And the last problem, second tangent of negative 4.474 will give us negative 77.4, because remember, inverse tangent function is also restricted, just like sine, inverse sine function, for the angle between negative pi over 2 and pi over 2, or negative 90 degrees and positive 90 degrees. 77.4 and negative 77.4, reference angle is 77.4 degrees. In the last example, we'll learn how to evaluate and simplify a composition that involves a trigonometric function and the inverse function. And the first example is sine of sine inverse 1/2. From the very first example, we remember that sine inverse of 1/2 is pi over 6. Therefore, sine of pi over 6 is equal to 1/2. The second example, sine inverse of sine 135 degrees. Because 135 degrees is equal to radical 2 over 2. Think about reference angle. Sine inverse of radical 2 over 2 will be angle between negative 90 and 90 degrees. It will be 45 degrees. I hope you find it helpful.